Hello everyone, I am Akash, founder and director of Prime Minister of Mathematics Amravati. In today's video, I am going to solve one question from CMI MSc PhD Entrance 2022 exam. This is one of the toughest exam on higher mathematics. CMI stands for Chennai Mathematics Institute. So question is, pick the correct statements from below. Options are option A, if f is continuous and bounded on open interval 0, 1, then f is uniformly continuous on open interval 0, 1. Second statement is if f is uniformly continuous on open interval 0, 1, then f is bounded on open interval 0, 1. Third statement is if f is continuous on open interval 0, 1 and right hand limit of f of x at 0 and left hand limit of f of x at 1 exists, then f is uniformly continuous on open interval 0, 1. Fourth statement is product of continuous and uniformly continuous functions on closed interval 0, 1 is uniformly continuous. So these are the four statements provided and we have to select those statements which are correct. So let's solve this question. We will verify one by one all statements. First statement is if f is continuous and bounded on open interval 0, 1, then f is uniformly continuous on open interval 0, 1. No, this is a false statement. I will provide counter example. For example, consider the function f of x equals to sine of 1 by x for x belongs to open interval 0. Then this function f is bounded and continuous on open interval 0. To see this, since minus 1 less or equals to sine theta less or equals to plus 1 for every theta belongs to R, from this inequality, it follows that f is bounded on open interval 0. Since from this inequality we see that sine function always takes values between minus 1 and plus 1. So this sine function, sine of 1 upon x, always takes values between minus 1 and plus 1. That is, f of x always takes values between minus 1 and plus 1. And this implies f is bounded on open interval 0, 1. Now, I will show that f is continuous on open interval 0, 1. To see this, let g of x equals to 1 by x and h of x equals to sin x for x belongs to open interval 0. Then it is clear that both g and h are continuous functions on open interval 0. Both functions has continuous graph, so both are continuous function on open interval 0. Here in this interval 0 is not included, so there is no problem for function 1 upon x. It is also a continuous function on open interval 0, 1. And sine function is also a continuous function on open interval 0, 1. And we know that composition of continuous function is again a continuous function. So from here, this implies h dot g, that is composition of h and g, which is defined as h of g of x, which is the function sine of 1 upon x. This is nothing but our f of x, is continuous function on open interval 0, 1. Since composition of continuous function is again a continuous function. Here h and g are continuous function on open interval 0, 1. So their composition, that is sine of 1 upon x, that is our function f of x, is continuous function on open interval 0. So up to now we have shown that our function f is bounded on open interval 0, 1 and f is continuous function on open interval 0. Now I will show that f is not uniformly continuous on open interval 0. To say this, for x which is equals to 2 upon twice n plus 1 pi and y which is equals to 1 upon 2n pi. Clearly, both these x and y belongs to open interval 0. We can verify it easily. Okay. Now, Consider the difference mod of x minus y. Just cross multiply, okay, 4n pi minus twice n plus 1 times pi upon twice n into twice n plus 1 pi square. Okay, 4n pi minus 2n pi, this will be 2n pi minus pi upon twice n into twice n plus 1 pi square. We can take pi common from numerator and that pi will be get cancelled with this. So what will remain? Mod of 2n minus 1 upon 2n into 2n plus 1 pi. And as this is a positive quantity, so no need to write modulus sign. Okay. So mod of x minus y is this quantity. Sorry, mod of x minus y is this quantity. And clearly this is less than delta for any delta greater than 0. Okay, this is less than delta. This is less than delta for any delta greater than 0 and sufficiently large n. Okay, we can take any value of delta, and as denominator is increasing in compared to the numerator, okay, denominator is increasing faster than numerator, so this value tends to 0 for sufficiently large n. This value tends to 0 as n tends to infinity. So this value is less than delta for any delta greater than 0. Okay, so we have for x comma y belongs to open interval 0 1, mod of x minus y less than delta. Now we need to verify that mod of f of x minus f of y is less than epsilon or not. Consider mod of f of x minus f of y. What will be this? F of x, f is this function sine of 1 upon x and x is this value. So substitute this x here. What we get when we substitute x here? We get sine of 1 upon this x 2 upon twice n plus 1 pi. After going to the numerator, this is equals to 2 upon twice n plus 1 twice n plus 1, this will go to the numerator, twice n plus 1 into pi by 2, and this is equals to sine of 2n pi by 2, that is n pi plus pi by 2. Okay, so this value is sine of n pi plus pi by 2, and this is always equals to plus 1 or minus 1. So what is f of x? Plus 1 or minus 1. So f of x takes value plus 1 or minus 1. Okay, so this is f of x. Now what is f of y? Substitute this y here. Okay, so sine of 1 upon y, so 1 upon 2n pi, so this will become sine of 2n pi, and sine of 2n pi is 0 for every n, so f of y is 0. So mod of f of x minus f of y will equals to 1, and this is greater or equals to epsilon for any epsilon less or equals to 1, or we can choose any value of epsilon. So for epsilon equals to 1 by 2. Okay, so we see that thus for epsilon equals to 1 by 2, there exists x comma y belongs to open interval 0 1 such that mod of x minus y less than delta, but mod of f of x minus f of y is greater than epsilon. So f is not uniformly continuous on open interval 0. So option A is wrong. That is, it is a false statement, and we have to choose the statement which are correct. Okay, so option A is discarded. Now we will see what is option B. What is option B? If f is uniformly continuous on open interval 0 1, then f is bounded on open interval 0 1. Yes, this is a true statement. It follows from result if a subset of R is bounded set and f from A to R is uniformly continuous function on A, then f is bounded on A. Okay. Now, A subset of R is bounded set. Clearly, open interval 0 1 is a bounded subset of R, and f from A to R is uniformly continuous function on A. And given that f is uniformly continuous function on A, then by this result f is bounded on A. Then f is bounded on open interval 0. So the statement in B is true, that is correct. Can you prove this general result? If you have any problem in the proof of this general result, then please comment on this video. I will make the separate video on the proof of this result. Okay, let's move to the next option. If f is continuous on open interval 0 1 and right hand limit of f of x at 0 and left hand limit of f of x at 1 exist, then f is uniformly continuous on open interval 0 1. Yes, this is also a true statement. This follows from result if f is continuous function on open interval AB and right hand limit of f of x at A and left hand limit of f of x at B exist, then f is uniformly continuous on open interval AB. F is uniformly continuous on open interval AB. Okay. Now, f is continuous on open interval AB. F is continuous on open interval AB. And right hand limit of f of x at A, right hand limit of f of x at A, left hand limit of f of x at B, left hand limit of f of x at B exist, then f is uniformly continuous on open interval AB. Then f is uniformly continuous on open interval this 0 1. So the statement in C follows from this result. Can you prove this result? I will give some hints. Since f is continuous function on open interval AB and both of these limits exist, so we can redefine the function f as f of x is equals to right hand limit of f of x at A if x equals to A equals to f of x if A less than x less than B, and equals to left hand limit of f of x at B if x equals to b. Okay. Then we see that this function f is defined on closed interval a b, and we can see that f is continuous on closed interval a b. Okay. So the function f has continuous extension on closed interval a b. The function f, this function f has continuous extension on closed interval a b because these both limits are exist. So by result, we use another result. If f is continuous function on closed interval a b, then f is uniformly continuous on closed interval a b. Okay. Now, as f is continuous function on closed interval a b, so by this result, f is uniformly continuous on closed interval a b. So this function f will be uniformly continuous on closed interval a b, and as it is uniformly continuous on closed interval a b, so it is uniformly continuous on every subset of closed interval a b. So it will be uniformly continuous on open interval a b. So f is uniformly continuous on open interval a b. So this proves this result, and from this result option C is true. Okay, f is uniformly continuous on open interval 0 1. Okay, so the only option is option D is left. What is option D? Product of continuous and uniformly continuous functions on closed interval 0 1 is uniformly continuous. Yes, this option is also true. To see this, let denote the continuous function by f and uniformly continuous function by g. So what we have, f is continuous function on closed interval 0 1 and g is uniformly continuous function on closed interval 0 1. Okay. Now use this result. If f is continuous function on closed interval ab, then f is uniformly continuous on closed interval ab, as f is continuous function on closed interval 0 1. So by this result, f is uniformly continuous on closed interval 0 1. So what we have, f is uniformly continuous on closed interval 0 1. Okay, and also we have g is uniformly continuous on closed interval 0 1. So g is uniformly continuous on closed interval 0 1. Okay, also by this result, if a subset of R is bounded set and f is uniformly continuous function on A, then f is bounded on A. F is uniformly continuous on this bounded set. So f is bounded on this set. Closed interval 0 1 is bounded subset of R. So as f is uniformly continuous on this bounded subset of R, so f is bounded on this set. And similarly g is bounded on this set. So overall what we have, f is uniformly continuous on closed interval 0 1 and it is bounded on closed interval 0 1, and g is uniformly continuous on closed interval 0 1 and it is bounded on closed interval 0 1. Okay, so we have this. Now we use the result. If f comma g are uniformly continuous and bounded functions on closed interval ab, then their product fg is uniformly continuous on closed interval ab. The same result also hold true if we replace closed interval ab by open interval ab. Okay, so we will use this result. Here we have f is uniformly continuous and bounded on closed interval 0 1, and similarly g is uniformly continuous and bounded on closed interval 0 1. So by this result, their product Fg is uniformly continuous on closed interval 0, 1. So the product Fg is uniformly continuous on closed interval 0, 1. Hence the statement in option D is true. Okay. Can you prove this result? I will give some hints, or else I prove it. Let's prove it. Okay. Since f comma g are bounded functions on closed interval AB, so there exists constant capital M greater than 0 such that mod of f of x less than capital M and mod of g of x less than capital M for every x belongs to closed interval AB. Okay. Since f and g are bounded functions on closed interval AB. Also, as given that f and g are uniformly continuous functions on closed interval AB, so by definition of uniform continuity, for every epsilon, hence for epsilon by 2m greater than 0, there exists delta greater than 0 such that mod of f of x minus f of y less than epsilon whenever mod of x minus y less than delta and mod of g of x minus g of y less than epsilon upon 2m, because we have selected epsilon as epsilon upon 2m, less than epsilon upon 2m whenever mod of x minus y less than delta. Since f and g are uniformly continuous function, so by definition we have used the definition of uniformly continuous function, uniform continuity of f and uniform continuity of g. Okay. Now consider mod of f of x g of x minus f of y g of y. This can be written as mod of f of x times g of x minus g of y times f of x plus g of y times f of x minus f of y times g of y. Okay. Clearly, left hand side equals to right hand side because these two terms get cancelled, and what is remain? F of x times g of x, f of x times g of x minus f of y times g of y. So LHS equals to RHS. And this part, triangle inequality of absolute value function, can be written as f of x times g of x minus g of y times f of x plus mod of g of y times f of x minus f of y times g of y. Okay. Now again, by taking f of x common and using the properties of absolute value function, this can be written as mod of f of x, we have taken common f of x. Okay. G of x minus g of y plus mod of g of y times f of x minus f of y. Okay. Now this is less than m, since f is bounded function on closed interval AB, and this is less than epsilon upon 2m by definition of uniform continuity of g. Okay. Plus this is less than m, since mod of g of x less than m for every x belongs to closed interval AB. So for y belongs to closed interval AB, mod of g of y less than m. So this is less than m, and this is less than epsilon upon 2m by definition of uniform continuity of f. When this will hold when mod of x minus y less than delta. Okay, so overall less than epsilon. Okay, so mod of f of x times g of x minus f of y times g of y less than epsilon when mod of x minus y less than delta. So it follows that the function fg is uniformly continuous function on closed interval ab. Since from this it follows that it is continuous on closed interval ab, and we know that a continuous function on closed interval ab is uniformly continuous function. So fg, the product fg is uniformly continuous on closed interval ab. So this will prove this general result, and from this result option D is true. So the answer of this question is B, C and D. Thank you for watching. If you found this video interesting and helpful, then please like and share this video and subscribe to my YouTube channel. This will motivate us to provide you more quality content. Thank you for watching.